Welcome students. Welcome to the lecture series on digital electronics. It is a subject in third semester, Diploma ETCE. The course code is ETCE/DE/S3. Today we are going to start lecture 16 of the lecture series. I am Paulu Sridhar, course coordinator and assistant professor, Department of ECE, Guru Nanak Institute of Technology. So before starting lecture 16, let us go through the course objectives and also in which unit we are going to deliver the lecture. So the subject digital electronics, which is in third semester Diploma ETCE, it consists of total number of lectures, 60 lectures are there. The credit is 4 and we are going through unit 2, that is Boolean algebra. In case of unit 2, today we will be starting unit 2.2, which is a sub unit of unit 2. The 2.2 unit consists of max term and min term, canonical form of the equations, and the simplifications of the Boolean expressions. Now, these are the course objectives. The course objectives are very important for the students because after the completion of the course, the students will be able to do everything that are written in the course objectives. The first course objective is do conversion of the number systems. Second one is understand the concept of the logic gates and its operation. 3 is design simple logic circuits using logic gates. 4 is design of combinational circuit. 5 is design of sequential circuit. 6 number is gain the comprehensive idea on various memory devices. 7 is understand the analog to digital conversion and digital to analog conversion techniques. 8th one is understand the different logic families and their comparison. Now you can see here that 2 and 3, this 2 and 3 points are in red color. That is, these two are the course objectives of this subunit. That is, this course objectives will be fulfilled after this lecture 16. That is, second one, understand the concept of the logic gates and its operation, and the third one is design simple logic circuits using logic gates. Now, logic gates are a very important part or topic in digital electronics subject because it gives us the base of designing all the logic circuits and also the base of the Boolean algebra, that is the logics. All depends on the logic gates, the truth tables that we are getting from the logic gates. Now, next is the small lecture plan of this particular lecture. This lecture comprises in unit 2 Boolean algebra, which consists of 10 lectures. We are continuing the subtopic, that is 2.2 max term and min term, canonical form of the equation, and the simplification of the Boolean expression. In this lecture, we will be going through some subtopics. First one is realization of the Boolean expression with logic gates. Next is max term and min term and the canonical form of equation, that is SOP and the POS form. SOP is sum of product and POS is product of sum, and also the standard forms in the case of the expressions. Next is expansion of the Boolean expression to SOP form, that is sum of the product form, that is in min terms and max terms. So let us start lecture 16, which here we will be studying max term and min terms and the canonical form of the equations and the simplifications of the Boolean expressions. Now, before starting lecture 16, let us have a quick recap of the previous lectures already we have studied or already we have heard about the other lectures. That is the lecture series from lecture 1 to 15 of the lecture series in digital electronics. Now, starting, we had studied about the syllabus and the course objectives, and also about the digital and the analog systems and the advantages and the disadvantages of the digital systems, how the logics are operating, and the applications of the logic circuits, that is the applications of the digital electronics in the field of the electronics and other fields. Next is, we have seen the types of the number system, and we have also done the conversions of one number system to the others. Next is, we have seen the complement forms, that is the 9s and the 10s complements, and also the how to represent the negative numbers. After this one, we have studied about the logic gates. In case of logic gates, we have studied about basic logic gates, then universal logic gates, and the exclusive logic gates. There we have seen about the applications of all the gates, which are very important, and which the logic gates form the basics of the digital electronics. Next is, we have seen about the various laws of the Boolean algebra, which was in unit number 2, and about all other laws, which includes the distribution law, the absorption law, the consensus laws, the De Morgan laws or the De Morgan theorems, and also how to demorganize is given expression, how to minimize the Boolean expressions. After all this, as Boolean algebra is a method for minimizing, we are coming to the second method of minimizing, that is the how to represent the Boolean expressions in SOP and POS forms, that is max terms and min terms. So let us start lecture number 16. That is the realization of the Boolean expression with the logic gates. Before starting of the realization of the Boolean expression with logic gates, let me tell you that a Boolean expression can be expressed in standard or canonical or expanded sum of product or product of sums, that is SOP form or the POS form, which we will be studying in the different slides of these lectures. Now let us start the realization of the Boolean expression with the logic gates. So Boolean expressions can be realized as hardware using logic gates. Conversely, hardware can be translated into Boolean expression for the analysis of the existing circuits. So first of all, let us start with converting Boolean expression to logic. So the expression we have taken is A dot B bar plus of A plus of B plus C bar. Now, the easiest way to convert a Boolean expression to a logic circuit is to start from the output and walk towards the input. So we will be starting to walk from the output and then we will be going to the input. Now this is the expression given, that is AB bar plus of A plus of B plus C bar. It has to be realized using the AOI logic, that is AND, OR and inverter logic. So start with the final expression. This is the final expression, that is AB bar plus of A plus of B plus C bar. Since it is a summation of 3 terms, this is the first term, second term, and this one is considered as a third term. So it is a summation of 3 terms. It must be the output of a 3 input OR gate. So it is the output of a 3 input OR gate. These are the 3 inputs of the OR gate. So we draw a OR gate with 3 inputs as this is shown here. These are the 3 inputs, A dot B bar, another one is A and another one is B plus C bar, and these are the 3 inputs of an OR gate, and the output is the A dot B bar plus of A plus of B plus C bar. Here again I am saying that this one, that is A dot B bar, is the first term we are considering this one is the second term and this one is the third term, and along with it, that is between them, we are having a plus sign. That is, the plus sign means OR gate. Okay, so the next step. Now what you see here, that A dot B bar must be the output of an inverter whose input is AB. Again, B plus C bar must be the output of an inverter whose input is B plus C. So we will be introducing two inverters. So two inverters are drawn here. What is the output? A dot B bar. Another output is B plus C bar. And what is the input of the inverter? First inverter, it is AB. Another input is B plus C. So this is the second step. Now we are going to the third step. Now see, now AB must be the, now let us see this one. Now this AB must be the output of a two input AND gate whose inputs are A and B, and also B plus C must be the output of a OR gate, that is two input OR gate whose inputs are B and C. So we draw it like this. See, this is the AND gate. Here there are two inputs A and B. Another, there is the OR gate. Here there are two inputs B and C. So the output is, here is AB, because AND gate means A dot of B and OR gate means B plus of C, that is plus sign. So ultimately this is the realization of the Boolean expression using the logic gates. Here we are using OR gate, AND gate and the inverter gate, and this is the ultimate expression. So we have seen how we are converting it. Okay, I hope this is clear to all of you. Now we will be explaining max term and min term and also the canonical form of the equations. Now we are starting with min terms. Now before starting the min terms, let me say some things which are very important in the case of the digital electronics. Now we have seen that Boolean expressions can be simplified algebraically, but being not a systematic method, we can never be sure whether the minimal expression obtained is the real minimal. The effectiveness of the algebraic simplification depends on our familiarity with and the ability to apply the algebraic rules, laws and the theorems. Now there is a term called K-map or the Carnot's map. This K-map is the other method or the systematic method of simplifying the Boolean expressions. The K-map is a chart or a graph composed of an arrangement of adjacent cells, each representing a particular combination of variables in a sum of product form, like a truth table. It means that the relationship between the logic inputs and the desired output will be shown in the K-map. Although a K-map can be used for problem solving for any number of variables, it becomes problematic for 5 or more variables. So this word K-map, for doing the K-map, we need the min terms and also the max terms. Normally, we can do the K-map using the min terms only. That is the sum of product. Now, any Boolean expression can be expressed in a standard or canonical or also expanded sum of product, that is SOP, or in a standard or canonical or expanded product of sum form. These are very important things. So let us start with the min terms. So in the later lectures, we will be learning about the K-map, but for now, we need to know what is a min term. For knowing the min terms, these are some points we also need to know. See, the first point is a binary variable can appear in either two forms. What are the two forms? First is it is normal form. That is, suppose there is a variable A, the normal form is A only, or it is complements form, that is A bar. Here there will be a bar. So suppose we are having a variable a. This can be present in either a form or a bar form. That is, these are the two forms that a variable can appear. Now consider three variables a, b and c that are combined by a AND operation. We will be seeing this one. We will be considering three variables. As I have already told you that a variable, suppose a, can occur in two forms. So first is the normal form, that is a, or in its complement form, a bar. Now we will be considering three variables a, b and c, and that will be combined with a AND operation. So what will be the number of possible combinations? It will be 2 to the power 3. That is 8 combinations. In decimal we can say 8 combinations means it will start from 0 to 7. That is 0, 1, 2, 3, 4, 5, 6 and 7. So let us see from the three variables how we can get the mean terms. Now look here, we are having three variables a, b and c, and this is the number, decimal number it is being showing, starting from 0 to 7, and these are the mean terms. So for mean terms, the binary words are formed by representing each non-complemented variable by a 1, that is this one suppose, and each complemented variable by a 0. So just look here, each of these terms a, b, c, it goes on like this, forming an AND operation is called the mean terms on the standard product. Now look here, these are the three variables a, b and c, and this is the number, and this is the mean term, and these are the names of the mean terms starting from M0 and it ends at M7. So first combination is 0, 0, 0. What does 0, 0 means? 0, 0, 0 means this is the 3-bit representation of 0 in decimal. This one is binary and this one is a decimal number. So this is the 3-bit representation of a decimal 0. So what I had told you earlier, that the binary words or this one is formed, or the mean terms are formed by representing each non-complemented variable by 1 and the complemented variable by 0. So this is a complemented variable. So this is 0 means a bar, this is 0 means b bar, and this is 0 means c bar. So this is a bar, b bar and c bar. And see here, this is mean term 0. Each subscript of the mean term means the decimal number. This decimal number is coming here as the mean term 0. This is mean term 0, mean term 1, mean term 2, mean term 3, 4, 5, 6 and 7. It goes on like this. So what will be this one? This term 0, 0, 1 means this is decimal number 1. So 0 means it is a bar. Again here 0 means it is b bar, and this is 1 means c. Similarly, this case 0, 1, 0 means the number 2. So this is 0 means a bar, this is 1 means b, and this is 0 means c bar. And this is mean term 2. Here let me draw one thing, that this 2 is coming here. Again this one is coming here. It goes on like this. That is, this one is coming here. That is, as a subscript we are adding it. As a subscript we are adding it. Now look here, in the fourth case, that is 0, 1, 1. That is the number 3. 3 is being presented in 3 bits. And the 3 bits means 3 variables a, b and c. So this one 0 means a bar, 1 means b, and 1 means C. So this is mean term 3. Again 3 is coming as a subscript here. Again 1 0 0, that is A. 1 means A, 0 means B bar, and 0 means C bar. This is 4. This is 4 means mean term 4. This 4 is coming as a subscript here. Next case is 1 0 1. That is number 5. So the mean term is A. For 1 it is A. For 0 it is B bar. And for 1 it is C. That is mean term 5. This 5 is coming as a subscript here. That is mean term 5. Next is 6. 6 is here. That is the number. So it is 1 1 0. 1 is A. B is 1 means B. C is 0 means C bar. That is M6. Next is 1 1 1. That is number 7 presented in 3 bits. So it is 1 means A, 1 means B, and 1 means C. So this is mean term 7. So this is written here that forming an AND operation. So here we have given dot sign. This is A bar dot B bar dot C bar. That is mean term 0. Each of this is having a dot between them. Again, see this one. This is A bar dot B bar dot C. This is mean term 1. This is A bar dot B dot C bar. That is mean term 2. Next is A bar B. A bar dot B dot C. That is mean term 3. Next is A dot B bar dot C bar. This is mean term 4. Next is A dot B bar dot C. This is mean term 5. And this is A dot B dot C bar. That is mean term 6. And last one is A dot B dot C. That is mean term 7. So there are, in case of 3 variables, there are 8 mean terms starting from mean term 0 to mean term 7. And remember one thing, that mean terms are always represented as small m. That is small m subscript of the number that is being presented. That is, suppose mean term 0 means 0 is present, will be going in as the subscript. Mean term 7 means 7 with, this is m7, this is 7 number is going as a subscript. And this is all followed by, or all inside it there is a AND operation going on. That is this is followed by some dot operations. That is, inside it there is a AND operation. So each of these terms, that is A, B, C, it goes on like this, forming an AND operation is called the mean terms on the standard product. So this is the mean terms. Next is the max terms. This mean terms and max terms are very important for deriving the K-map, which we will be studying in the later lectures. Now, max terms. Again, there are 3 variables. This is the number, that is the decimal number, that has been represented in 3 bits. And this is the max term. And the max term starts from M0 to M7. And remember one thing, that the max terms, unlike the mean terms, are always represented in capital letter M. In the case of the mean terms, it was represented in small m. But in max terms, it is represented in capital M. That is capital M, subscript of the number that is being represented. Now, see each of these terms, A plus B plus C, and it goes on like this, forming an OR operation is called the max terms or the standard sum. Inside, between them, that is, there is a OR operation, that is plus sign is there. That's why it is a standard sum. So let us start from first combination. Here A, B and C are the 3 variables, and this is the number and this is the max term. Now for max terms, the binary words are formed by representing each non-complemented variable by 0 and each complemented variable by 1. So unlike the mean term, the max term is just the opposite of the mean term. Here in the case of the mean term, 1 was equal to, suppose there C is equal to 1, so it would have been C, but here 1 is represented by C bar and 0 is represented by C only. Like this 0 is C. Now let us look here. The first combination 0, 0, 0. So what will be the max term? A plus B plus C, and this is equal to max term 0. That is 0 is shifted in the subscript. Next is 0, 0, 1. That is the number is 1. So it is A plus B plus C bar. So it is mean term 1. Next is 0, 1, 0. That is the number 2. That is A plus B bar plus C. It is max term 2. Next is 0, 1, 1. That is the number 3. So it is A plus B bar plus C bar. That is max term 3. Next is 1, 0, 0. That is number 4. That is A bar plus of B plus of C. That is max term 4. Next is 1, 0, 1. That is max term 5. That is A bar plus of B plus of C bar. That is max term 5. Next is 1, 1, 0. That is 6th number. That is A bar plus B bar plus C. That is max term 6. Next is 1, 1 and 1. That is the number 7. So it is max term is A bar plus of B bar plus of C bar. So this is max term 7. So these are the max terms starting from 0 to 7. Now listen one thing, that suppose here the variable number is 3. What are the 3 variables? A, B and C. If the variable would have been 4, that is suppose A, B, C, D or X, Y, Z, like this we are taking. So the number of mean terms on the max term will be 2 to the power 4, that is 16. In this case, as there is 3 variable, so the number of the mean terms of the max term is 8, that is 2 to the power 3. If the variable number is 2, that is suppose we are writing the truth table for A and B. So the number of mean terms will be 4. Why? Because it is 2 to the power 2, that is 4 mean terms. So this was the max terms. Now the next slide is the max term and the mean term relation. There is a certain relation between the max term and the mean term. What is the relation? Each mean term is the complement of its max term and vice versa. That is, you can say that small of mn is equal to capital of Mn, complement of capital of Mn. Also you can say capital of Mn is equal to complement of small of Mn. So both of these are related. That is, suppose if we are having mean term 3, if we want to find max term 3, then we have to do the complement of mean term 3. Then we can get the max term 3. Similarly, if we have max term 4, suppose we want to find mean term 4, then we will be doing the complement of the max term 4, then we will be getting the mean term 4. In this, the complements, we will be applying the De Morgan's theorem. Then we can find the mean terms and also the max term. I hope this is clear to all of you. Next slide is very important. That is, this slide is the canonical sum of the product expression. This is a very important slide which explains the sum of product. We have seen what is mean term, what is the max term. Now we will see what is the sum of product. Now look here, that it is the logical sum of the mean terms derived from the rows of the truth table for which the value of the function is 1. Similarly, it is also called sum of the product, that is SOP. The canonical sum of the product expression can be given in a compact form by listing the decimal codes in correspondence with the mean term containing a function value of 1. This is a very important line. that for which the value of the function is 1. This is a very important thing. In case of the sum of product, we will be considering the values of the function where the value is 1. Now we will be writing one truth table, and we will be writing the corresponding values of the function, and we will be finding the mean terms as well as the max terms. Let us see one example. That is how to find the canonical form of the product expression. Now we will be finding the mean terms from the truth table. Suppose this is the truth table, that is 3 variable truth table is given, that is a, b and c are the 3 variables, and f is the function. We have to find the, first of all we have to find the Boolean expression, and after that from the Boolean expression we have to find the mean terms. This is our task. What is our task? We have to find the Boolean expression, and from the Boolean expression we have to find the mean terms. Hope this is clear. The task we are going to solve. So these are the 3 variables a, b and c. The combinations are given and the corresponding values of the function are given. For this value, that is 0, 0, 0, the value is 0. For 0, 0, 1, the value is 1. For 0, 1, 0, the value is 0. The combination is 0, 1, 1, the value is 0. Next is 1, 0, 0, the value is 1. Next is 1, 0, 1, the value is 0. Next is 1, 1, 0, the value is 0. Next is 1, 1, 1, the value is 1. This is the example. We are taking these values we are taking it as an example. The values can change also. This is just an example, and we have just taken an example to find the Boolean expression, that is the sum of the product. We will be finding the sum of the product, and also the sum of the product means we will be finding the mean terms. So just see here, just see, I am highlighting the combinations where the value is 1, because we will be taking these combinations. This is 1, this is 1, and this is also 1. Already it was told in the previous slide that we will be taking the function values where the values are 1. So this is the function values, this is the function values, and we are taking the combinations where the function values are 1. So see here, the Boolean expression can be formed by considering the mean terms where f1 is equal to 1 and taking the OR of all of them. So what we will do, now we will be taking f is equal to this one first. This one is, first consider this value. The value of function is 1 here. So what will be the value? This is 0, 0, 1 means a bar, b bar and c. So write a bar, b bar and c. And what it is told that we will be taking OR in between them. So again this is the plus means OR. So again take this combination, that is 1, 0, 0. 1, 0, 0 means a, then b bar, then c bar. That is a, b bar, c bar. Next again it is followed by a plus sign, that is we are taking the OR operation, plus a, b and c. That is this combination, that is 1, 1 and 1. Already in the previous slide it is told that in case of the mean terms we will be taking the values where the variable values are 1. That is 1 means a and 0 means a bar. Suppose the value of 1 is 1, sorry, the value of a is 1, so we will be taking a, and if the value of a is 0, we will be taking a bar. That is the case. Here also we are taking the same things. That is f is equal to, considering this combination, it is a bar, b bar and c. This one is a, b bar, c bar. This one is a, b and c. So this form is the standard form, or also called the sum of product. See, each of this this one, and this one. That is A bar, B bar, C. This is a product. Again, A dot B bar dot C bar is a product. Again, A dot B dot C is a product. And between them, there is a plus sign. That is sum of product. That's why it is called sum of product. I hope that sum of product you've understood why it is named as sum of product. Next is this one. Now this denotes, this is mean term 1. This is mean term 1. So I am writing mean term 1. This is mean term 4. So I am writing 4. And this is mean term 7. Already this mean term we have seen in the previous slides. That what does each of this corresponds to which mean terms? This is mean term 1 because this is decimal value 1, 0, 0, 1. Next is A, B bar, C bar. This is 4. Next one is A, B and C. That is 1, 1 and 1. This is decimal number 7. So this is mean term 7. So this is the combination of M1, that is mean term 1, mean term 4 and mean term 7. That is the sum of product form. This one is the sum of product form. So this is the summation of mean term 1 or the combination of mean term 1 plus mean term 4 plus mean term 7. So this is also called the canonical form. This is the canonical form that is represented by arrow sign. That is this one, M1 plus M4 plus M7 is the canonical form. Now you can, as this one is a sum, so you can replace it by a summation sign. And this one is summation small m in brackets 1, 4, 7. This is the representation in the case of the mean terms. Always in case of the mean terms, as this is sum of the product, so this is represented as summation sign, and it is this m bracket 1, 4 and 7. Why? Because this mean term, it is a summation of mean term 1, 4 and 7. Also you can write it like this, that is summation of mean terms 1, 4 and 7. Or if you don't write m, then also it is okay. If you don't write m, suppose, then also it is okay. So this was the how to find the mean terms from the truth table. I hope this is clear to all of you. Next is canonical form of sum expression. Now it is the logical product of all the max terms derived from the rows of the truth table, for which the value of the function is 0. This is a very important line. For which the value of the function is 0. It is also called the product of sum, that is POS. The canonical product of sum expression can be given in a compact form by listing the decimal codes corresponding to the max terms containing a function value of 0. The highlighted portions are very important in this slide. Now consider that we will be taking now the values of the function where the value is 0. That is the canonical form in the case of the sum expression. Here we will be taking the values where the function is having 0 value. Next is, here we have to find the max term from the truth table. Now this is a truth table. This is the truth table where A, B and C are the 3 variables and F is the function. That is, F is having the values corresponding to the combinations. So let us see, 0, 0, 0, the value is 0. The value of the function is 0. 0, 0, 1, the value is 1. 0, 1, 0, the value of the function is 0. 0, 1, 1, it is 0. 1, 0, 0, it is 1. 1, 0, 1, it is 0. And 1, 1, 1, it is 0. And 1, 1, 1, it is 1. So we have to find the Boolean expression of F, and also from here we have to find the max terms. So this is the first point. Boolean expression can be formed by considering the max terms where f is equal to 0 and also taking the end of all the terms. This is a very important line, or the statement is very important. That is, we will be considering the max terms where f is equal to 0 and also taking the end of all the terms. That is all the max terms. The max terms we will be getting, we will be taking the end of all the max terms. So consider this case because here, consider this case because here the value is 0. The value of f is 0. Here also the value of f is 0. This case also, this case and this case. So we will be considering first case, second case, third, fourth and fifth case. There are 5 max terms in this particular Boolean expression. The Boolean expression we will be getting. So what we will do, and we will be taking and between the max terms. So we can write f is equal to, this one is, in case of max terms, 0, the value of 0. That is, suppose a is having the value of 0, so it is a, and if it is 1, the value of a is 1, then it is a bar. So it is, the combinations are a, b and c. The combinations are 0, 0, 0. So it is a plus of b plus of c. In between them, there will be an and. So dot of this one. That is a plus of b bar plus of c. Next is again dot, then this term. That is a plus of b bar plus of c bar. Again dot, that is product of, that is a bar plus of b plus of c bar. Next is this case, dot of a bar plus of b bar plus of c. So this is the first max term, second max term, third max term, fourth and fifth max term. So this particular expression is the standard form. So this f is equal to this term is the Boolean expression of this particular truth table. And this Boolean expression can be also called as the standard form or the product of sum. Why this is product of sum? See, these individual terms are the sums and they are, in between them there is a product. So what we can say, that is, this is the max term 0, this one is max term 0, this one is max term 2, this one is max term 3, and this one is max term 5, and this one is max term 6. This one, here, and this one. So this one is nothing but, this max term 0 means this is represented as number decimal 0. So this is max term 0. This one is max term 2, as this is 0, 1, 0 means 2, that is max term 2. This is max term 3, that is 0, 1, 1. It is the decimal 3 which is represented in 3 bit. Next is 5. 5 means 1, 0, 1. So max term 5, and this is 1, 1, 0, that is max term 6. This is the canonical form. The presentation of the Boolean expression in max term is the canonical form. Now this is product of sum. In between them there is a product. This m0, dot of m2, dot of m3, dot of m5 and dot of m6. And remember one thing, it's very important, I've already told you, but again I'm telling you that this max terms are represented in capital letters. That is capital M. Always it is universal in nature. That is capital M. In case of mean terms, it will be small m and subscript of is the number. In case of the max term, it will be capital M and subscript of the number. So as this is a product, so we can give the sign of product. This one is the product sign, that is this sign is the product sign. This is the product sign, and in brackets the max terms that are present, that is 0, 2, 3, 5 and 6. This is the presentation of the max terms. So from now on, if it is written like this, that is summation is written, that is summation of mean terms, like this is written, then we will be considering this one as the mean terms, and if this sign is there, that is product form, and there is the max terms are present here, then it is a max term. This one is a mean term presentation and this one is a max term presentation. I hope this is clear to all of you. Now let us go to the next slide. Now we will see how we will be doing the expansion of a Boolean expression to SOP form. This is also very important. Now there are few points. We need to see the points. The following steps are followed for the expansion of the Boolean expression in the SOP form, in the standard SOP form. The first one is write down all the terms. This is the first point. Write down all the terms. Next is, if one or more variables are missing in any term, then expand the term by multiplying it with the sum of each of the missing variables and its complement. Next one is drop the redundant terms. Now we will apply these points in an expression and see how we will be finding the max terms and the mean terms. Now, before doing it, remember one thing, the words I'm saying, these are very important words. Now, a standard SOP form can always be converted to a POS form by treating the missing mean terms of the SOP form as the max terms of the POS form. Again, I'm repeating it, how we can convert an SOP to a POS form by treating the missing mean terms of the SOP form as the max terms of the POS form. Similarly, a standard POS form, that is product of sum form, can always be converted to a standard SOP form, that is sum of product form, by treating the missing max terms of the POS form as the mean terms of the corresponding SOP form. Now the statement I had told you, I will be applying this, or we will be applying this in the next example. Let us see the example. Now we will be expanding A bar plus of B bar to mean terms and max terms, and this falls under the expansion of a Boolean expression to SOP form. So just see the solution. This is the given expression is a two variable function. What are the two variables? A and B. In the first term, this one, there is a bar. So here the variable B is missing. Similarly, the second term, that is B, that is B bar, the variable A is missing. So what we will be doing here, in the first term, as the variable B is missing, so we will multiply it with B plus of B bar, this one. Next, in the second term, there is B bar, but A is missing. So what we will be doing? We will be multiplying it with A plus of A bar. This is analogous to the points I told you earlier in the previous slide. So we have multiplied A bar with B plus of B bar and plus of B bar. We have multiplied it with A plus of A bar. Now this two, this is equal to 1. Again, this one is also equal to 1. So just we are multiplying it again, that is expanding it. That is, it becomes A bar B plus of A bar B bar plus of B bar A plus of B bar A bar. Now we are just arranging it, that is A bar B plus of A bar B bar plus of A B bar plus of A bar B. Next is, here what we can write, that is A bar B plus of A bar B bar plus of A B bar. Why we have excluded this one? Because it occurs 2 times. This is occurring 2 times. So we can write 1 time. This also we have seen in the previous slide, how we can ignore this A bar B bar. If 2 A bar B bar is present, we can ignore 1 and we can write A bar B bar. So we have written it A bar B plus of A bar B bar plus of A B bar. Now this one is 0, 1 plus of 0, 0 plus of 1, 0. Now this one is 0, 1 means 1. It is the 2-bit presentation of 1. So it is M1. Next is 0, 0, that is 0, mean term 0. The next is 1, 0, that is 2-bit presentation of decimal 2, that is mean term 2. As I had told you earlier also that 2 variable means there will be 4 mean terms. But here in this particular expression, only 3 mean terms are present. And we have find out from the Boolean expressions. By solving the Boolean expression, we can find out the mean terms. So here only mean term 0, mean term 1 and mean term 2 are present. So we are writing it in summation form, that is equal to summation of mean terms 0, 1 and 2. We've written it like this. Now, as I had already told you, from here we can find the max terms. How? This mean term 3 is missing in the SOP form. This is the SOP form, that is the sum of product form. This is the sum of product form. See here, this mean term 3 is absent in this SOP form or missing in the SOP form. So this max term M3 will be present in the POS form. Hence, the POS form is product of M3. This is the product of M3. That is, so we can also write that the mean terms are 0, 1 and 2 and the max term is max term 3. So this is solved. So we have come to the end of this lecture and I'm very thankful to all of you for listening to me. Thank you again.